We are going to go for a marathon video today. We might break 20 minutes, but we are going to solve a bunch of different equations, and my friend Musty's here to help us, right? Yes, we can do it. So we've learned quite a few different types of equations, and so let's just get started, I guess. So here are two radical equations, and you can pause the video and solve these on your own if you think you can, or you could skip ahead to the next section if you think you're comfortable with these, but I'll solve each of them. So let's start with this cubed root guy. So for both of these, the goal is going to be to, first of all, try to get this square root thing alone, or cubed root thing, called a radical, and then we raise both sides to some sort of power. And so in this case, to get the cubed root alone, I think I need to add 7 to both sides. And that gives us 18. Then I'll divide both sides by 2, which gives me 9. And now I want to raise both sides to the third power. And so that is kind of the key move, raising both sides to the third power. That undoes x minus, or the cube root here, and 9 to the third power is just some big number, right? 729. And to finish, I'd add 6 to both sides, and we get our answer. So that's a basic idea of a radical equation, at some point raising it to a power. One thing you have to be aware of is when you do that move of raising both sides to a power, sometimes it introduces answers that aren't really answers, that are called extraneous solutions. And so you can check for extraneous solutions a couple different ways. The most obvious way is to just put the number in, 735 in for x, and see if it makes this original equation true. It's a little bit big in this problem, but it's doable. Another option, and this is an option for any type of equation, is you can also check or even find answers by graphing. And so here I graphed the left-hand side, that's the cubed root in this graph in red, and then I graphed the right-hand side, which was just the number 11. And where those things intersect, the x-coordinate is our answer. And in this case, there is a legitimate intersection at 735, and so this really is a solution. So that's another strategy you might want to keep in mind. This one with the square root is a little bit more challenging. It's already got a radical alone, and so I can immediately square both sides. On the left-hand side, the squared undoes square root. That was by design. On the right-hand side, x plus 4 squared means x plus 4 times x plus 4, and that's going to be a bit of a nightmare. You're going to need to FOIL that out. And so why don't we do that? X times x is x squared, 4x and another 4x gives me 8x's, 4 times 4 is 16, and now I've got a quadratic equation, x's, x squares, and so forth. To solve these, you typically push everything to one side, set it equal to 0, and then either use the quadratic formula or factor. In this case, this factors into x plus 5 times x plus 1, and then I can split that up into two separate equations, x plus 5 equals 0 and x plus 1 equals 0, and solve each of those. So, yikes. If I solve this one, I get negative 5, and if I solve this one, I get negative 1. Now, we need to check if these are extraneous. And so to do that, if you plug a negative 5 in, you end up getting on this side, the square root of 1 is 1. And on this side, a negative 5 plus 4 is negative 1. And those aren't the same. And so this guy is an extraneous solution, doesn't count. If you plug a negative 1 in, both sides end up being the same thing of 3. And if we look at a picture, we can also see that there's only one intersection in this graph, and that's here at negative 1. The negative 5 that we got for an x would be an intersection if this red graph was upside down. It would intersect down here. But anyway, that's radical equations. Let's look at exponential equations. So again, here are two. If you wanted to try to solve them on your own, you can. If not, it's fine. Here we go. So first one, to solve this, my initial goal is going to be to try to get this chunk with the e to the x alone. And so to do that, I'm going to subtract 1 from both sides, and then I'll divide both sides by 3, and that gives me e to the stuff equals 4. And the key move in exponential equations is to take the log of both sides. And which choice of base you use for log depends on the problem. And so this one has an e in it, and so I'm going to choose the natural log to take on both sides. And when you do that, on the left-hand side, that undoes e raised to the, that was on purpose. So we have 5x plus 4 equals natural log of 4. And then I've got a few moves to do to get x completely alone. I've got to subtract 4 from both sides and divide both sides by 5. And so if you want your answer exactly, then you can write it like that. Usually we want to then type that into a calculator and get an approximation. And so if you typed it in, you get this negative 0.05 sort of number. Let's look at the other one. So over here, if you try to get this 4 to the x part alone, you'd have to subtract a 2 from both sides. And then you might notice that 64 is a power of 4. 64 happens to be 4 cubed, and so if you knew that and wrote it as 4 cubed, then you could say, all right, x minus 5 has to equal 3, and add a 5 to both sides, and you've got one of your answers is 8. If you don't notice that, because I mean, it's not obvious that 64 is 4 cubed, another approach, if we go back to that step, is we could take the log of both sides. And this being a 4 raised to the problem, I would like to take log base 4 of both sides. And so on the left-hand side, that's just going to become x minus 5. On the right-hand side, log base 4 of 64 happens to be the number 3. It's the power that's required to bring 4 up to 64 is 3. Or on one of these calculators, you could type log of 64 divided by log of 4 and get your 3. So either way, we end up with an 8 as an answer. So that's exponential equations. Whew. All right, log equations. So to solve a log equation, key move is to exponentiate both sides. Exponents, logs, they're inverses of each other. So the next move that I would do in this situation, I'm not going to move myself anymore. It's kind of awkward. Next thing I would do is to raise both sides on top of power of 3. And so that looks like this, 3 to the log base 3 and 3 to the 7th. And the point of that is on this side, those are inverses and they undo each other. And you're left with 2x minus 5. And on this side, 3 to the 7th is just a number. It's not one I had memorized. Definitely used 3 to the 7th on the calculator and got 2187. And then a few follow-up moves, adding 5 and dividing by 2, and we get our answer of 1096. Notice again, we can solve this by graphing. Graph the left-hand side and the right-hand side, and there's one intersection, happens to be at 1096. All right, we are nearing the end. There are 2 more types of equations to solve. We've got a rational equation and a trig equation. So rational equations are equations with fractions, and a key move that I teach even my Algebra 1 students to do is to get rid of fractions in a problem, to multiply by the denominator. If there's more than one denominator, you might have to multiply by the greatest common denominator. So in this case, I would suggest as a first move, multiplying both sides by x plus 3. So on the left-hand side, when I multiply x plus 3 by this fraction, the x plus 3 and the x plus 3 cancel out, and I'm left with just the top. When I multiply x by plus 3 times 7, that's going to require the distributive property. I chose to do that in a second step. Over here, x plus 3 times x plus 5, that's another foiling that is going to have to happen. And so at this point, you should distribute the 7, you should FOIL, and that gives you a bit of a mess. You've got a lot of different terms, x's, numbers, squareds, and so on. Um, Again, it's a quadratic equation, and so you shove all those things to one side, equal to 0. I did that by subtracting an x and subtracting 7x's and adding 2 and subtracting 21 from both sides, and assuming I didn't make any mistakes, I ended up with x squared minus 4, which can be factored, x plus 2 times x minus 2 if you want, or because it doesn't have an x term, this is also one that's easier to just solve by adding a 4 to both sides, taking the square root, and realizing that when you take the square root, there are 2 possible answers, plus or minus 2. So, real quick, here's the picture of that. And you can see the rational expression here is that curve that has asymptotes, vertical and horizontal, and then the line x plus 5 is here in blue, and they happen to intersect right here, which I believe is 2 and negative 2. Wait a minute. I think I may have made a mistake. I'm not sure what that mistake is, and this video is running long, so I'm going to have to look into that and see what I did wrong. But maybe I typed in the equation wrong. Ah, I did. This is x minus 2, and I graphed x plus 2. All right, never mind. I think our work on the other page is right, but my picture was bad. So, oh well. One last type of equation, and that is a trig equation. And so here I have 4 cosine of x plus 8 equals 11. And I decided to kind of spoil it by showing you the graph right away because I wanted to remind you that trig equations are unique. They have an infinite number of solutions. So there's an intersection here, 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 and so on. And there'd be no way you could list them all. And so what we usually do is we list 2 of them, and then we write it as plus 360k if you're working in degrees, or 2 pi k if you're working in radians. And so one intersection's here at 41 degrees, the next intersection is 318 degrees, and then after that you get a 401 here, which is 360 degrees after that. And so this would be our final answer. Now, how do we get that if we aren't just relying on Desmos to solve it for us? Well, let's see. So, yeah, spoiler, answer's still here. My initial goal is to get cosine of x alone, and so I'm going to subtract an 8 and add or divide by 4. So subtracting 8 gives me 3, dividing by 4 gives me 3/4. And then the key move to undo trig is to use the inverse trig equations. So sometimes they're called arc cosines on your calculator. That's when you press second cosine or second sine. And so over here, those just undo each other and give you x. And this is now something you definitely need to type into a calculator. Second cosine of 3/4. When you do that, you get your first answer. And in this case, that is 41.4 degrees. But in order to find all of the answers, you need to know some things about how trig works. I've been trying to get you to remember that sines are kind of like heights, cosines are like widths, and tangents are kind of like slopes. And how that helps us in this particular problem is I've got one answer here in 41 degrees, that's here in quadrant 1, and it's a cosine problem. And so it's a width, and I need to know what other width gives me a positive 3/4 width. And so that would be something down here in quadrant 4. And so to find that, just get out of the way. Thank you, Mr. Lord. To find that, I need to realize, all right, this 41 degrees is going to be 41 short of 360. And so I do a little subtraction. 360 minus 41 gives me 318. And 318.6, yeah. Anyhow, there is the 2 answers that we get that are within 0 to 360. And then because you could always go around the circle once and a little bit more, that's where that plus 360k comes in. So, wow, I didn't think we were going to make it, but we did. So, I hope you enjoyed that review. Please let me know if you have any trouble with a particular type of equation, or if you need help writing an equation that works out nicely, because that's not always obvious how to do that. Anyway, I'll catch you in the next video.